Components of a solar electric system. 1. Solar panels. The heart of a solar electric system is the solar panel itself. There are various types of solar panel, and I will describe them all in detail later on. Solar panels, or, more accurately, photovoltaic solar panels, generate electricity from the sun. The more powerful the sun's energy, the more power you get, although solar panels continue to generate small amounts of electricity in the shade. Most solar panels are made up of individual solar cells, connected together. A typical solar cell will only produce around half a volt, so by connecting them together in series inside the panel, a more useful voltage is achieved. Most solar panels are rated as 12-volt solar panels, although higher voltage panels are also available. A 12-volt solar panel produces around 14 to 18 volts when put under load. This allows a single solar panel to charge up a 12-volt battery. Incidentally, if you connect a voltmeter up to a solar panel when it is not under load, you may well see voltage readings of up to 26 volts. This is normal in an open circuit on a solar panel. As soon as you connect the solar panel into a circuit, this voltage level will drop to around 14 to 18 volts. Solar panels can be linked together to create a solar array. Connecting multiple panels together allows you to produce a higher current or to run at a higher voltage. Connecting the panels in series allows a solar array to run at a higher voltage. Typically, 24 volts or 48 volts in a standalone system, or up to several hundred volts in a grid tie system connecting the panels in parallel allows a solar array to produce more power while maintaining the same voltage as the individual panels. When you connect multiple panels together, the power of the overall system increases, irrespective of whether they are connected in series or in parallel in a solar array where the solar panels are connected in series. You add the voltages of each panel together and add the wattage of each panel together to calculate the maximum amount of power and voltage the solar array will generate. In a solar array where the panels are connected in parallel, you take the average voltage of all the solar panels and you add the wattage of each panel to calculate the maximum amount of power the solar array will generate. 2. Batteries. Except in a grid tie system, where the solar array connects directly to an inverter, solar panels rarely power electrical equipment directly. This is because the amount of power the solar panel collects varies depending on the strength of sunlight. This makes the power source too variable for most electrical equipment to cope with. In a grid tie system, the inverter handles this variability. If demand outstrips supply, you will get power from both the grid and your solar system. For a standalone or a grid fallback system, batteries store the energy and provide a constant power source for your electrical equipment. Typically, this energy is stored in deep-cycle, lead-acid batteries. These look similar to car batteries but have a different internal design. This design allows them to be heavily discharged and recharged several hundred times over. Most lead-acid batteries are 6-volt or 12-volt batteries and, like solar panels, these can be connected together to form a larger battery bank. Like solar panels, multiple batteries used in series increase the capacity and the voltage of a battery bank. Multiple batteries connected in parallel increase the capacity whilst keeping the voltage the same. 3. Controller. If you are using batteries, your solar electric system is going to require a controller in order to manage the flow of electricity, the current, into and out of the battery. If your system overcharges the batteries, this will damage and eventually destroy them. Likewise, if your system completely discharges the batteries, this will quite rapidly destroy them. A solar controller prevents this from happening. There are a few instances where a small solar electric system does not require a controller. An example of this is a small, battery top-up, solar panel that is used to keep a car battery in peak condition when the car is not being used. These solar panels are too small to damage the battery when the battery is fully charged. In the majority of instances, however, a solar electric system will require a controller in order to manage the charge and discharge of batteries and keep them in good condition. 4. Inverter. The electricity generated by a solar electric system is direct current, DC. Electricity from the grid is high voltage alternating current, AC. If you are planning to run equipment that runs from grid voltage electricity from your solar electric system, you will need an inverter to convert the current from DC to AC and convert the voltage to the same voltage as you get from the grid. Traditionally, there is usually one central inverter in a solar system, either connecting directly to the solar array in a grid tie system, or to the battery pack in an off-grid system. A more recent invention has been the microinverter. Microinverters are connected to individual solar panels so that each individual panel provides a high-voltage alternating current. Solar panels with microinverters are typically only used with grid tie systems and are not suitable for systems with battery backup. For grid tie systems, they do offer some significant benefits over the more traditional, big-box, inverter, although the upfront cost is currently higher. Inverters are a big subject all on their own. I will come back to describe them in much more detail later on in the book. 5. Electrical devices. The final element of your solar electric system is the devices you plan to power. Theoretically, anything that you can power with electricity can be powered by solar. However, many electrical devices are very power-hungry, which makes running them on solar energy very expensive. Of course, this may not be so much an issue if you are installing a grid tie system. If you have very energy-intensive appliances that you only use for short periods, the impact to your system is low. In comparison, running high-power appliances on an off-grid system means you have to have a more powerful off-grid solar energy system to cope with the peak demand. Low-voltage devices. Most off-grid solar systems run at low voltages. Unless you are planning a pure grid tie installation, you may wish to consider running at least some of your devices directly from your DC supply rather than running everything through an inverter. This has the benefit of greater efficiency. Thanks to the caravanning and boating communities, lots of equipment is available to run from a 12-volt or 24-volt supply. Light bulbs, refrigerators, ovens, kettles, toasters, coffee machines, hair dryers, vacuum cleaners, televisions, radios, air conditioning units, washing machines and laptop computers are all available to run on 12-volt or 24-volt power. In addition, thanks to the recent uptake in solar installations, some specialist manufacturers are building ultra-low energy appliances, such as refrigerators, freezers and washing machines, specifically for people installing solar and wind turbine systems. You can also charge up most portable items such as MP3 players and mobile phones from a 12-volt supply. High-voltage devices. If running everything at low voltage is not an option, or if you are using a grid tie system, you use an inverter to run your electrical devices. Connecting everything together, a standalone system. The simplified block diagram above shows a simple standalone solar electric system. Whilst the detail will vary, this design forms the basis of most standalone systems and is typical of the installations you will find in caravans, boats and buildings that do not have a conventional power supply. This design provides both low-voltage DC power for running smaller electrical devices and appliances such as laptop computers and lighting, plus a higher voltage AC supply for running larger devices such as larger televisions and kitchen appliances. The solar panels provide the energy, which is fed into the solar controller. The solar controller charges the batteries. The controller also supplies power to the low-voltage devices, using either the solar panels or the batteries as the source of this power. The AC inverter takes its power directly from the battery and provides the high-voltage AC power supply.